Hello and welcome to the UFS webinar. This webinar is hosted by the National Weather Service, Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. I'm Stacy McKell and I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you would like to present at this webinar, you can email your recommendations to ufs.modeling@noaa.gov, and we'll take your suggestions into consideration. Due to the high number of attendees, you'll be in listen-only mode during the event, and you will not be able to unmute. If you have any questions now or during the event, please submit them on the Google document that will be provided in the chat box. Presentations last about 45 minutes, followed by questions and answers for 15 minutes. Type your questions on the Google document during the presentation. Okay. Today's presentation is addressing tropical variabilities and connective gray zone representation in NOAA's Unified Forecast System, also known as UFS. Before we get started, I would like to show you all how to sign up for the webinar notifications and how to view archived information. If you go to the UFS community.org portal, scroll down to the events section and you'll see webinars listed on the page. Archived information will also be on this page. Also, UFS, these webinars will be recorded and made available on this UFS portal. So, today's speaker, Lisa Bengston, will be introduced by Jeff Whitaker, and I will turn it over to Jeff.
Thanks, Stacy. I'm pleased to introduce our speaker today, Dr. Lisa Bengston, who's a research scientist at the NOAA Physical Sciences Laboratory. She joined us here at PSL in 2017, and for 11 years before that, she was working at the research branch of the Swedish Meteorological and Hydrological Institute, SMHI. She's been with Ceres since joining us, but just last week she actually joined the federal workforce, so we're very excited about that. Her research is focused mainly on improving numerical weather prediction forecasts through the development of physical, stochastic, and deterministic parameterizations. So Lisa, over to you.
Okay, thank you. So I see my screen on my end. Does it look okay for you too?
Yes, it does.
Okay. Well, thank you very much, Jeff. So I would like to start off by acknowledging a lot of collaborators that I've had the pleasure to work with in the last 5 years here at PSL. And also collaborations with EMC, NSF EMC, and our international community, ECMWF, and RMI Belgium. So I'll jump right in, and I'd like to start off with this nice animation that I borrowed from Yuanming Cheng here at PSL. It shows that in the tropics, convection closely interacts with synoptic scale features, like here. So convectively coupled equatorial waves are seen as sort of blue contours propagating eastward in this animation. And I like it. I like this animation because you can kind of clearly see the connection between the tropics and the mid-latitudes through the interaction between convectively coupled waves acting as a Rossby wave source. So Rossby waves are, the proxy for Rossby waves are here seen as green contours. So this kind of interaction, which leads to teleconnection, is shown nicely in the schematic diagram by Christina Sten and her colleagues. So convectively coupled equatorial waves, including the MJO, acts as a Rossby wave source and can influence weather at mid-latitudes. As you know, the weather on the west coast of the United States is highly influenced by the tropical variability over the Pacific. But even downstream over Europe, changes in the MJO patterns can change the blocking patterns over the Atlantic, leading to high pressure systems over Scandinavia. So if you have a perfect simulation in the tropics, how much forecast skill could you gain in the mid-latitudes due to these kind of teleconnections? Juliana Diaz and her colleagues here at PSL, they published an interesting study last year where they used the UFS to estimate how much forecast skill can be gained in the mid-latitudes if the representation in the tropics is perfect. Perfect. So here they nudged an analysis over the tropics to simulate this perfect tropics and estimated a sort of 20 to 40% reduction of mean absolute error can be seen in the mid-latitudes in week 4. Also in weeks 3 and 4, they found a 2 to 4 times larger precipitation anomaly pattern correlation. So without a doubt, convective parameterization plays a key role for model representation of tropical variability. Let's see if I can move this bar here. So for the UFS global application, the GFS shows that the following aspects for the modeling of, maybe I can lower, sorry, I had this bar in my, so modeling of tropical space-time variability and precipitation frequent distribution is through studies that I have made over the years, we show that the moisture profile in initial state is important. Also the cloud depth and coupling to upper level dynamics, the representation of convective organization or mesoscale feedbacks in convection, moisture sensitivity in the convection closure, as well as stochasticity. So for the, oh, maybe I can't, sorry. No, I can't advance this, maybe I needed to keep that up. Oh, there we go, okay. So for seasonal, sub-seasonal to seasonal prediction, the ECMWF model have been very successful at modeling convectively coupled equatorial waves, and they have a very good representation of tropical variability in their forecast system. So in this study that I will talk about first, we implemented the ECMWF IFS convection scheme into the GFS. And then we also studied running the model with the IFS initial conditions and with their convection scheme to kind of detangle to see which aspects would be beneficial for improving tropical variability within the GFS. So just to mention briefly some implementation details, since physical processes interact with one another, it's not possible to sort of plug and play one well-tuned parameterization scheme into another physics suite without carefully addressing how various schemes interact. So integrating the ECMWF cumulus convection scheme with other physics schemes within the GFS, it took about a year, perhaps on and off about a year, and it's mainly in regards to how convection and boundary layer mass flux are unified, how convective clouds are seen by radiation, as well as liquid water detrained from the resolved clouds to the resolved clouds are handled. So I'm not going to go into too much details on the implementation details, but I'm happy to discuss this at any time. It's also part of this paper. Okay. So the first question we ask here is that the initial condition, or is it the convective parameterization that contributes to better tropical variability in the ECMWF model? So here we use GFS version 15. The top panel here shows, so all of this is a 6-hour forecast. So early on in the forecast, and these are the observations, TRIM and CMORPH. So they're in quite good agreement. I'd say we can be pretty confident that these two data sets are very similar. And then on this row here, we have the GFS version 15 using the GFS initial conditions. And at this row, we have GFS version 15 using the IFS initial conditions. So you can see right off the bat of a 6-hour forecast, the the GFS, when using IFS initial conditions, has better space-time variability seen in these Wheeler-Kelati's type diagrams, in particular probably in the Kelvin wave band, but also somewhat of westward propagating waves. The difference with between having two different convection schemes could be seen comparing these two columns, and that difference is quite small. Here's after 6 hours. After 60 hours, then you can see that the spectra is a little bit more flat. So, for instance, yeah, I think all the model runs are more flat. The difference you see now is perhaps bigger depending on the convection scheme you use, and in particular with GFS, with the GFS initial conditions, that you see along the Kelvin wave band that the convective parameterization plays a pretty big role in maintaining some of this variability in the Kelvin wave modes. It's not trivial to detangle, you know, the reason why the IFS initial condition is better for this particular analysis. If it's they have better data simulation algorithm, they use more or better observations, or if they have a longer window, or if it's also, you know, the background forecast, or the background forecast, the first guess forecast is of course highly influenced by the physics that you use. So if you have a better representation of physics, it could also influence the initial condition. So to try to detangle this a little bit, we looked at the replay increments. So we replayed GFS version 15 to the IFS analysis with the two respective convection schemes. And we find that the GFS 15 is too dry in the lower troposphere, and replacing the convection scheme doesn't really change the picture in the lower boundary layer. So red areas here indicate where the IFS analysis is moister than the 6-hour forecast. It does look like there's some difference in the lower troposphere, mid-troposphere, which could be, well, which is definitely attributed to the cumulus convection scheme. But the lower boundary layer is still too dry, even when we have the IFS shallow and deep convection schemes. So to understand further, so the ECMWF analysis, it could be moisture than the forecast due to difference in use of humidity observations in the IFS data simulation itself, or the IFS model background first guess forecast used in data simulation is moister than the GFS version 15 forecast. So to try to understand this further, we now look at the operational system. So here is operational ECMWF version 45R, and this is the GFS version 15. So we can see with blue colors here is that means that ECMWF analysis is working to dry the tropical the tropical lower troposphere, where the first guess forecast is too moist. And in general is kind of opposite that we see within the GFS version 15. So I think it suggests that it's mainly due to the model forecast step. The forecast is too dry in the GFS, but it's as we saw before, it's not only attributed to the cumulus convection scheme. It could also be due to other physics, such as the PBL scheme, differences in surface fluxes, or for instance the differences in the precipitation microphysics. Next we look at how the different convection schemes, so GFS version 15 with the SAS and the IFS convection scheme, how does that interact with the dynamics? So here we have precipitation to the left, 850 hectopascal divergence and 200 hectopascal divergence to the right. And then you can see, for instance, with the so the top row is air interim, and then the control GFS 15 here, and with the IFS convection at the bottom. So the 200 upper level divergence field matches quite well between the GFS version 15 with the IFS convection, Of course, it should be noted the ERA interim also uses the IFS convection scheme, so that might be part of the reason that there's a better match. But clearly, the IFS convection scheme has an ability to influence the upper level divergence when it is within the GFS. So Maria plotted these coherence plots. So we looked at the coherence between precipitation and divergence along these tropical wave bands. So you can see that comparing the GFS version 15 with the GFS version 15 and that has the IFS convection scheme, you have much stronger coherence squared between the precipitation and the divergence here at 850 along these wave modes. So I think it's having a convection reach deeper is an important part for that interaction. So to understand that further, we looked at the number of times convection is called between the different schemes, and we find that this varies substantially. So in the top row we have deep convection in SAS and deep convection from IFS, and this is sort of the number of times convection is called within on average within a 6-hour time frame. So you can see it's almost more than double along the tropical band with the IFS convection, whereas with shallow convection, the GFS SAS scheme triggered shallow convection more frequently than the IFS. And the IFS convection also have this what they call mid-level convection. So in general, I think, and this is part of the reason we have stronger interaction with upper level dynamics using the IFS convection scheme. Okay, I would like to switch gears a little bit and talk about a parameterization of organized tropical convection that I've been working on for quite many years now. So we published this in 2021, and I also have sort of a series of papers leading up to this this work on sort of using cellular automata to address self-organization and aspects of cumulus convection that we cannot address with bulk mass flux schemes. So in my mind, the main motivation for using cellular automata is that it possesses self-organization, and birth-death processes are suitable for modeling of organized physical systems such as atmospheric convection. It introduces 3D effects of convection, which is generally modeled using a 1D plume model. Also, stochastic representation of the convection has been shown beneficial to address statistical fluctuations in cloud number or intensity, or I would say maybe statistical fluctuation on the subgrid, so subgrid variability. And for seasonal and climate prediction, stochastic cumulus convection can be viewed as noise-induced forcing. So with the cellular automata, there's a lot of choices, I'd say. There's a lot of degrees of freedom, so there's some important considerations to make when implementing this and to address cumulus convection. One is the model forcing to the CA. You can see, for instance, that a cellular automata pattern on the global grid can look vastly different depending on if you let it run freely or if you're forcing it with some model field. And then, of course, the evolution rule set of the CA itself. You can have a deterministic rule set or a probabilistic rule set. Here's an example from our paper in 2013. This figure was made by Martin Steinheimer, where we used a probabilistic rule set following direction of the wind to evolve the cellular automata in time. The time and space scales of the CA are also very important, because you can see you could have rather small scales, and you could have these broad, really sort of global scales, and it's gonna these kind of correlation scales is gonna matter a lot for depending on your application. And I think the most important is then how you use it, the coupling to convection itself. So if we have a bulk mass flux scheme, so you have bulk quantities that are provided. In this case, then we use the CA to parameterize this convective subgrid and cross-grid organization in terms of how the resolved flow would kind of respond to more coherent structure on the subgrid. So in this sense, you could have a cellular automata self-organizing across adjacent model grid boxes. And in this sense, say, okay, we have, because we had convection here that was coherent, we're also gonna have convection in the adjacent grid box that is more coherent. And this coherent structure is gonna have a feedback on a convection scheme. And we addressed that by sensitivity study. We had entrainment, closure, or the triggering in nearby environment. So for instance, if you have convection here, but not here, now you could trigger convection in this grid box because of this self-organization provided by the CA. And here's just a snapshot of what it could look like when as the CA is sort of averaged onto the model grid box. So this flow chart is adapted from Mapes and Neal from 2011, and they had this 2D org field sitting here, and kind of the same idea that that's a positive feedback. So we forced the cellular automata with the subgrid rain evaporation to mimic this idea of cold pools developing. So that's kind of the main idea. Here we look at the spatial autocovariance of total precipitation and the impact of using the CA following this entrainment, triggering, closure ideas. So the solid black line here is our control run. This was also done with GFS version 15. And you can see that with all these organization feedback mechanism, we do get more coherent structure on the as an impact of precipitation, and mainly when you perhaps not surprisingly allow the CA to trigger convection in nearby environments. And this also seems to better match the observed trim data set on the same grid. So we look at the impact on I guess convectively coupled equatorial waves. So this is a Hohmiller diagram which shows some space-time organization on various scales. You have sort of MGO phase speeds early on, and you have a lot of Kelvin wave activity later on. And Juliana Diaz helped me for this paper we wrote plot these radon transformation, plus you have the variance of the precipitation along different phase speeds. So you compute the variance along phase speeds, and that's what we did with the observations, is this gray curve. And here's a reference of GFS version 15. And then we ran a set of ensemble experiments, and you can see that the observation kind of have this peak phase speed along 15 meters per second, which is associated with the Kelvin waves. And it seems like all the model forecasts are a bit slow. They have kind of peak phase speeds that are a little bit slower than the 15 meters per second. But when you have these more coherent structures from the CA trigger, it tends to speed up the phase speed and better match the observations. We could also look at the impact of stochastic physics by perturbing the tendencies using the SPPT method. And you can see in this case, some members speed up and some slow down, and it's kind of what we would expect with a stochastic scheme like that. In this sense, we get a more systematic response by the stochastic organization scheme. So why does the sort of enhanced subgrid organization enhance phase speed? And I think we analyzed this in terms of changes in gross moist stability and also in the vertical heating profiles. So the normalized gross moist stability, it's been shown to influence Kelvin wave phase speed through the interaction between latent heat release and with low level moisture convergence. So without going into too much detail here, it's essentially we see an increase of this measure normal gross moist stability, in particular when we allow the CA to trigger in a nearby environment. And this has been shown in other studies to be related to the split between resolved and subgrid precipitation fraction. And in general, if you have a lower, a reduction in large-scale precipitation and an increase in convective precipitation, it tends to change this measure. And we think that this is the main reason why we see a shift in phase space, more shift towards convective precipitation, which is, logical, since we tend to trigger more and for longer times to have these more coherent structures. We did look also at the vertical heating profiles, but that did not change substantially with this method. Okay, so another study we did recently, and we also used cellular automata, but in this case, we did not have a bulk mass flux scheme, but we'd rather used a spectral plume distribution. This was done using the Chikira and Sugiyama cumulus convection scheme. And in this case, the CA then provides a distribution of a plume number and plume size. So just a kind of schematic idea of what this can provide, and we use that to sort of sample this plume number for a number of convective plumes in the Chikira-Sugiyama scheme. And doing so, we also looked at the frequency distribution of precipitation with various options of stochastic physics. So we had like a ISPPT is when we apply perturbations onto the convective tendencies only. And then when we did that in combination with the CA approach of sampling for the convection scheme, you see that the precipitation frequency distribution shifts and sort of better match the observations. In that study, this is kind of the pattern that we used. Okay, so the last study I'd like to talk about was actually very recently published as an early online release in the Monthly Weather Review. And here we kind of tie it all together in a sense. Going back to this picture, I talked a lot about this triggering in nearby environment, that this is an effective way of using the cellular automata for subgrid organization in a bulk mass flux scheme. In terms of closure, then the way I've been thinking about is that more coherent structure on the subgrid by the CA and the self-organization, it would result in a larger area fraction. However, in traditional cumulus convection schemes, it's sort of assumed that the area coverage of all the cloud elements in a grid box is much smaller than the grid box itself. And under this assumption, area fraction is actually negligible. So it's assumed to be it is just assumed to be negligible in the equation. So instead, the average effect of the full ensemble of possible cloud elements in the grid box is sort of under this quasi-equilibrium assumption with the resolved large-scale variables under this sort of steady state assumption. So under this quasi-equilibrium steady state assumption, then more organization would have to be associated with an increase of the mass flux at cloud base, but not necessarily explicitly to a larger due to a larger area fraction. It's simply just kind of an increase of the mass flux at cloud base to represent a positive feedback. But as we go to higher resolution, this quasi-equilibrium assumption is not valid any longer. And that's what led us to this work, where we now introduce a prognostic stochastic closure. So we actually no longer assume negligible area fraction. We introduce a prognostic equation for the updraft area fraction based on a moisture budget equation. And this is following work by Luc Girard and Jean-François Gélin from the mid-2000s. And then we used the cellular automata to enhance the area fraction in case of more subgrid scale organization. So this is the budget equation that we use. There's some observational support to have a prognostic, a physical equation for the prognostic area fraction. So this is from Christian Jacob and their team. They use these vertically pointing radar observations from Darwin, Australia. And they see that there's a strong relationship between the convective area fraction and the tropical precipitation rain rate. And they also look at the vertical distribution of the mass flux. This is the mass flux can be seen as a product between the area fraction and vertical velocity. And mainly it's the area fraction that dictates the shape of the mass flux profile rather than the vertical velocity. And this area fraction then has a close relationship to moisture convergence than what it has to CAPE that we indicate here. So having a moisture budget equation for the area fraction, I think is reasonable, and also that the area fraction can be used to describe mass flux of a cloud base, which would show a close relationship with the enhanced precipitation rain rate. And there's been a lot of studies that have demonstrated that moisture feedbacks are essential for convectively coupled equatorial wave initiation and propagation. And in particular, the MGO is improved when convection is made more sensitive to environmental moisture. There's also a recent study by Liu et al. That indicates that the MGO predictions largely improved if shallow convection is not activated until a time composite of moisture convergence over grid box turns positive. So we explore the impact of our prognostic closure, looking at convectively coupled equatorial waves and MJO prediction. So here, Maria again plotted this coherence spectra between low-level moisture convergence and precipitation. And you can see with this is now the GFS version 16, and this is ERA 5, and this is the prognostic closure. You can see that the coherence between the moisture flux convergence and precip is enhanced along the tropical wave modes using this new closure. And given the, I guess the studies in the literature suggesting that there's an enhanced coupling between moisture and subgrid convection is important for MGO prediction. We did the MGO case study, and you can see that it's in this particular case we have a very positive impact of using this prognostic closure. So the red curve here is the GFS version 16 control, and the MGO kind of stagnates over I think it's the Western Pacific, whereas we get somewhat better propagation using this new prognostic closure, and also the amplitude, it picks up better already, I'd say already here after day 5, with stronger amplitude and phase. We looked at some sensitivity because this was just one case, and now we used the cellular automata, run 5 additional forecasts with the CA additional term to this prognostic closure. So the CA can enhance the area fraction when there's more subgrid organization. But since it's initialized in a stochastic way, there's going to be a slow response, a nonlinear response with increased lead time. And you can see that they start to diverge probably around day 10 or so, maybe a little earlier. After about a week, they start to diverge. And in general, like some members are really good, some are a little bit slower, and some actually kind of stagnates. I think that's probably this member that has a very large amplitude. But I think it provides a good amount of spread due to simple feedbacks in the convective parameterization. So the question is if this impact of the CA in this case can be viewed as a noise-induced forcing, or do we see a systematic enhancement of subgrid precipitation? And that's why we see this shift in MGO, phase speed, for instance, or amplitude. So in this top graph, I show the area fraction. So say that's orange curve is the area fraction of the from our moisture budget equation, which is you can see as a function of time. So this is forecast lead time. So this is simply the area fraction. Then the green curve is the area fraction with the CA contribution as an additive term. And the CA systematically enhances the area fraction throughout time. But when we look at the response in precipitation, you can see that it's not a systematic increase. There's some strong variability in time. This goes out to 90 days. So I think that while the updraft area fraction is systematically enhanced due to subgrid organization feedbacks, the response in precipitation is not systematic. And in that sense, I think part of what we see here can be viewed as more of a noise-induced forcing rather than a systematic sort of enhancement of convective precipitation. I hope that makes sense. Okay, so the last topic I'd like to talk about is some scale adaptive considerations. So a common way of, as we go to high resolution, is to kind of scale down the mass flux by the sort of term 1 minus the area fraction squared. And I borrowed this schematic from George Grell. He points out that, you know, this is simply a scaling factor. Convection is much more 3D than just the vertical eddy transports. It doesn't account for all of the convection. And the assumption is if you scale down the mass flux by this factor, assumption is that at say 3 kilometers, the resolved dynamics will be able to resolve the convective motion and take over. But we see in GFS version 16, when I ran at 25 kilometers and at 3 kilometers, in some areas over the Pacific or in weakly forced environment, resolved convection is not picked up by the dynamics when the subgrid fluxes are scaled down. So I shared this at the UFS EPIC summer meeting, that with these considerations, the devil is in the details in some way. So in our new formulation, the mass flux at cloud base is constituted by this kind of scaling as well, but also the area fraction times the updraft velocity. And the updraft velocity itself is scale adaptive because of this buoyancy term in the formulation. So you can see if we break down the cloud-based mass flux in terms of updraft vertical velocity and updraft area fraction, it's actually perhaps more so the scale adaptiveness of the updraft velocity that plays a role into the scale adaptive nature of the cloud-based mass flux. So we looked at this using the new prognostic closure that I proposed in this study, and also compared here 25 kilometers and 3 kilometers. And now you can see that in general we get better scaling. They match better, these two. It picks up, for instance, over South American and Central Pacific. And I think in general that is because with this prognostic closure we keep more subgrid precip than what the control is doing. So I think I'm going to stop here. I think maybe I don't read through all my conclusions, but rather I'm happy to take any questions that you may have.
Thank you so much, Lisa. That was very informative, very interesting information. The Google document for any questions was put in the chat box. So if you pull up the chat box, you could pull up the Google documents. And Lisa, are you able to see the questions so that you can answer your?
Yeah, let me see. Oops, I can.
There you go.
Maybe I go back. So chat. Let me see. Questions. Chat.
Okay. So people will be putting their questions in, and you can read them and answer them as you see fit.
Okay, so if the convective precipitation is staying nearly the same in the mean, but the updraft is enhanced, have the model changes essentially increase the efficiency of the precip to have? Yeah, I would say to Elizabeth's question, I don't know if everybody, should I repeat the question perhaps loudly? So she asks, if the convective precipitation is staying nearly the same in the mean, but the updraft is enhanced, have the model changes essentially increased the efficiency of the precip to have greater mass flux? I think that's a good question. I think the answer is not about the precipitation efficiency. I think that's something else, but is essentially the contribution of the CA in this last study is a small enhancement to the area fraction. I think I would definitely, if I had used the subgrid organization to enhance the area fraction more, you would see a response in more, you would have stronger convection, you would have stronger precipitation as a consequence. But I think because it's a rather small increase, what we see is sort of the model responding to that, and then that's why we don't see a systematic enhancement of convective precipitation. But I think that's what you're asking. So my answer is essentially like, had I had a larger increase to the mass flux, then we would have seen an increase in the mean subgrid convective precip. I guess I can't really hear, right, if that was a okay response. Maybe I'll just, yeah, I'll follow up with Elizabeth after. So again, the next question is, how much, if any, of this work is being tested with the latest UFS coupled prototypes? This last piece that I was talking about with the prognostic area fraction, we are now testing with the prototype 8 physics. I didn't show any of those results because we just started that work. So far, I've only done atmosphere-only simulations, but once I have some satisfactory results in prototype 8 atmosphere only, I'll move on to the coupled prototype 8.
Okay, we're going to wait for some more questions. If anybody has any questions, please type them. There we go. They usually come, as people think of them, and we give them time to type so that, they can get it together.
I would say no. The lower tropospheric dry bias, I think after all these studies, I don't think it's necessarily due to convection on its own. I think it's actually more related to the PBL scheme, or the coupling between the PBL and the surface scheme and the surface fluxes. So I think we tried quite many updates within the shallow convection and deep convection scheme to see if we could address this dry bias, but my inclination is that it's probably related to the PBL scheme. This is kind of a cool way of interacting. I guess if there's no more questions, I can give you 15 minutes back. Oh, here comes one. So one of the questions was, what do you want to do next? That's a good question. I think there's a couple avenues to explore. One would be maybe so with this prognostic closure, we essentially only address the prognostic area fraction, but I think it could be interesting to go further and have a prognostic evolution also of the updraft velocity, and that would kind of constitute the entire mass flux profile. And in that case, I think the prognostic evolution of the updraft velocity should also be a prognostic stochastic equation to make the scheme fully kind of stochastic. So that's one thing I'm exploring. Other than that, I think it's right now a lot of testing, evaluation, just to see how it can be integrated in the prototype 8 physics suite. I missed some of the presentation. Did you address computational load? Does this dramatically increase? No, the CA does not. The CA does not increase runtime. It's just like a 2D field, so I think it's relatively cheap. I have not addressed. I have not looked at the increase in runtime by adding one prognostic variable, so I would have to do that. Does the CA increase the deep convection? No, I could. Here's the CA has a very a very small impact on the heating profile. The CA in this case is almost neutral, and if I take only the grid points where the CA is active, so this is a tropical mean, all grid points, but if I take only the grid points where the CA is active, you can see that in general it enhances the heating in all these kind of configurations, trigger, entrainment, and closure. It has a positive effect, but the CA trigger is not applied on shallow convection. It has no impact in the shallow convective scheme. So when the CA in a grid box where you have a CA, it enhances convection. How do I go back to the?
Are there any other questions coming in? Okay, doesn't seem like there are any other questions. If anyone has any questions, please quickly type them into the Google document that is shared on the screen. If not, Lisa, thank you very much for your presentation. It was very informative, and I'm sure I could speak for everyone. They enjoyed it. Okay.
Thank you very much.
You're welcome. And I want to thank Jeff also for being a part of this to introduce you. Jeff, thank you very much. And without any further ado, we will adjourn this presentation. Thanks, everybody, and we will see you again next month.
Yeah, thank you so much. Bye.
Bye. Thank you.